Hello, everyone. I hope you had a great day so far. Let's start today's discussion, and hopefully we can finish the chapter 1 today and move on to chapter 2. Uh, I can't promise chapter 2 would be more interesting. Probably that would be like the same fundamental definitions or stuff. But that's important because we are going to need those when we move on to the more complicated and more kind of like a practical concept that we are going to have uh, through the semester. Now, so far, we talked about the probability. We learned about the axiomatic approach. We talked about some definition, the set, subsets, event, elements, some of the special sets, sample space, null set, singleton, and we learn about how like the basic mathematical kind of like process when we talk about sets, like the union or that or situation that we talk about when we wanted to like add the probabilities of two sets or the multiplication, which was the AND situation. And we talked about the complement of the sets, which was the not happening kind of like situation. And we actually had a very simple example of a sequential probability, which was two experiments following each other. And the result was based on what we have at the result of the whole experiment was based on the result of the first step of our system, that flip a coin and then rolling a dice situation. Okay, now in this session, we are going to go over some of the basic rules. A bunch of them are the same as what we learned before for that mathematical kind of like process for the sets, but there are going to be some new stuff too. Now, first, is there any question about what we covered so far? So no confusion, no question. Are you kind of like hesitating to ask, or I did a good job to teach those concepts? No?
I think you did a good job.
Oh, thank you. Okay, so let's move on to this session. What the first basic rule that we want to talk about is the equality of the events. We know all the events are some sort of subsets, so that means the equality in mathematical terms would be the equality of the sets. Okay? Now, when we want to say the two events are equal or two sets are equal, that means all the members of the first set are the members of the other, okay? Which we had that basically in the definition of the subset. So the first one is the subset of the other. And the second one also is a subset of the first one. So it goes both ways. Now, what that means when we say, if, for example, in this slide, we mentioned E and F as our events or sets. When we say E is a subset of F, okay, what that means when we wanted to also say F is also subset of an E, okay? More sophisticated way to say that is that E is a subset of F, okay, and E complement and F would not share any element. So there is no elements outside of E or F, okay, that happen to be in the second set. All the members are the same. That means these two sets or these two events are equal to each other. Are we good? Now, one thing that we learned, and we called it as an AND situation or multiplication, is basically the sophisticated way to say that is the intersection. Okay? When we talk about intersection, for example, between the event E and F, we are talking about the situation when both of those events happening at the same time. We said that it's an AND situation. So if both of the events happen at the same time, okay, the result would be the intersection of the two events. Now, from element perspective, okay, from the element perspective, that means the intersection of E and F is all the elements that the two sets would share with each other. Okay, the overlap of the two events would be the intersection. We called it multiplication before. Now the actual term is intersection. Okay, now next one, the union of events. We called it summation before. That or situation. Okay, the union of event, for example, E and F, is when either one of them would happen. Okay, so from element perspective, from element perspective, that means all the members in E and in F could happen. So all the members all together. Are we good? That would be the union of the two events or the two sets. Now, again, we already talked about that. It's a kind of like a review. The complement of an event is when that event would not happen. That means all the possible outcomes that of that event, in this case, event E, okay, would not occur. So it's going to be sample space minus E. Are we good? And we already know that the E and E complement would not share any elements. So the intersection of the E and E complement is going to be null set. What about the union? What's going to be the union of E and E complement? The whole sample space. Because in another definition, we said set, a special set, a specific set, and the complement of that set are set partition. That means they are mutually exclusive. They don't share any element. The intersection is null. Okay? And altogether, the union is going to be the sample space. Mutually exclusive, collectively exhaustive at the same time. Are we good? I'm using different kind of like definitions, so you kind of like warm up and you see from the different perspective. Now, go on. You can do that. Okay. When we say the difference between an event, which is kind of like the same as subtraction in like a scalar math, is when the possible outcome are all the elements in E minus the shared elements. So E minus F is the outcome or elements in E, okay, without the elements in F. Now, if they are mutually exclusive, they don't share any element. But in general term, we can assume mutual exclusivity. So what's happened, E minus F is going to be the E, okay, from mathematical perspective, it's going to be the E minus the intersection of the F and E complement. Are we good? Now, the definition of certainty and impossibility are very important. When we say some outcome is certain, that means that is going to happen. So the probability is 1. I'm reviewing what we talked about before. And the impossible one is that there is no way that that element would happen, or in another perspective, the non-occurrence of that outcome is certain. Are we good? That would be the probability 0. And mutually exclusive, we already talked about that. That means they don't share any element. That means there is no way that both of them would happen. So if E and F are mutually exclusive, under any condition, we don't have the outcome when both of them are going to happen. That means the intersection of the two is null set. Are we good? Now, based on those definitions, we have some basic laws mathematically. They are quite straightforward if you follow the definition. So they are not very complicated, to be honest. But they are the base of all the mathematical derivation that you will do over the sets. Now, these are not about the probability or calculating anything. We have some sets. We don't know what's happening inside them. Okay? Actually, we don't run any experiment. Okay? Sometimes we want to draw a mathematical derivation to basically model the relation between these two sets. Okay? These basic rules or basic laws help us to run those derivations because they are the one that always true. You cannot assume any specific case when you're dealing with a certain experiment. So you need to kind of consider all the possible situation. One example was when you don't know anything about the experiment, you cannot assume mutual exclusivity between the subsets because you don't know what's happening. You should consider a general case. They could share or they could not share. Okay, any element. But these rules are always true. Now, the first one, very straightforward. Okay, the complement of an event is going to be the same as event. So complement of E complement, for example, is going to be the E. And it's just straightforward. This is the definition of a complement. Okay? The union of a set and its complement, we already again talked about that in previous slide as an example, is going to be the sample space because they are set partition. Union of a set and the complement of the set is going to be the sample space. Intersection of any event and sample space is going to be the event because sample space is our universe. The shared element with a specific event, which is the subset, and the universe is going to be that event. Are we good? Now, we already talked about the mutual exclusivity of an event and event complement. So the intersection of the two, the intersection of any type of event and the event complement is going to be a null set. Now you might think, okay, these are like child play, okay? It's not very complicated, but when you want to prove a statement regarding the sets, these are the one that help you to manage through the process of proving a certain kind of like condition. You're going to see that in your first homework. One of the problems is to find out if, like in a statement or a relation between the two sets, okay, for a specific case, is true or false. Now you use these basic laws to manage through the process of finding out if that statement is true or false. These are the rules that is always happening. The rest you cannot consider that is always true. Okay, the rest of the conditions. Very good. Now, there are some commutative rules between those kind of like mathematical processes. Union and intersection have that characteristics. So the union of E and F is going to be equal to the union of F and E. Very straightforward. Okay? Same goes for the intersection. The intersection of the E and F is going to be equal to the intersection of the F and E. Now, you see that I use another notation for the intersection. That is also accepted when you want to like write mathematically in a correct kind of like notations. So you can use the here's my thanks. You can use that notation of the inner. Come on, come on. Oh, the delay. You can use the previous notation, okay, or you can simply use the kind of like a multiplication notation in your when you wanted to like display the intersection. Are we good? Now, again, I want to emphasize that sets are not a scalar. How you deal with the scalar numbers, like 2 plus 2 or like 2 times 2, this is not happening when you're dealing with sets. Two different universe. Okay? Now, another part is associative laws. So, when you have the union of E with the union of F and G, okay, you can replace the kind of like the, you can change the whole kind of situation and consider it as union of E and F, now union with G. Okay? So these are very helpful. You might think they are very simple, but these are very helpful. I want to emphasize that. Same goes for the intersection. Intersection of E with intersection of F and G is going to be the same as intersection of E and F with G. Very good? Next one. Distribution. You can expand some of those formulas, some of those mathematical derivation. Now, the intersection of E and F union with H, you can expand it to the intersection of union of E and H and union of F and H. They could be expanded. Now, there is a very good chance that it would have like a lot of delay, but let's say we had an E. Come on. So intersection of E and F like let's say this is E, this is F, this is H. The intersection of E and F is going to be this part. It is going to show you, so don't worry about that. With a union of H. And if you go through another way, so we have again E, F, and H. It is going to be the union of, if we calculate the union of E and H, which is, come on, this part, and the union of F and H, which is this part. What happened? Oh, you can see that the intersection of the two is, again, the same. I hope you can see that, actually. It's good that we are living. Do you see what happened? Yeah. I hope you understand what I said about the distribution of that first one. And the same goes for the second one. The union of E and F is going intersection with H is going to be the intersection of E and H union with an intersection of F and H. We have additional identity law that says basically any event is the union of that event with an auxiliary event like F. Okay, so we have event F to help us. Okay, it could be any event. The intersection of our target event with that ancillary event F, union with the intersection of the E with complement of the F is going to be E. Is that clear what I mean? So you have an event E, you consider any type of event F. Okay? That is a bit of rain. I don't know why I go through that all of it's wrong. You have event E, okay? And you have a complementary, I don't care, event F. And we have our sample space. Now, the intersection of E and F is this part, right? F complement is this part. Everything outside of that. The intersection of E and F complement is this part. The union of them is going to be E. Sorry? The union is going to be E, yeah. So you can basically create an additional identity for the E using any type of ancillary event. Very good. Another one, the event E, which we already know is the intersection of our event with sample space, okay, is going to be equal to the event E, intersection of event E with the union of F and F complement, because we know that F and F complement is going to be the sample space. Correct? Now, we already learned about that distribution law, that when you have E intersection with F union F complement, you can expand. That could be expanded into the intersection of E and F, union of the intersection of E and F complement. Very good. So these are the base laws that we have for dealing with the set when it comes to mathematical derivation. Any questions so far? Is that clear? You guys can see that, right? Those, yeah. I don't want the podium to be blocking the board. Okay. Now, one of the interesting one is the De Morgan law. Okay. The De Morgan's law says that the complement, which also, again, I used another notation that is accepted. Instead of that C, we just can use a prime. The complement of A union B is equal to the intersection of the A complement and B complement. You can see the Venn diagram of why these two are equal to each other. So the left-hand side is the complement of the union of the two events. We have the union of event, and then we take a complement. Okay. On the other side, we have A complement intersection with B complement. We find the A complement. We found the B complement at the second Venn diagram. Intersection is going to be the same. Good. So this is a De Morgan's law. Any question? Now you might think that don't take a genius to find out what's happening, but you know, someone put the name on that law. Way to be humble. Now, we talked about these are the base law you need to remember. So I'm going to move forward to more practical kind of like situation. When you talk about the probability and calculation of the probability for some basic situation that we could have. One, which was actually one of the examples that we saw before, discussed before, is the sequential probability. Okay? Sequential probability is when two experiments or multiple experiments, not just two, happen in a sequence. Very easy, isn't it? Okay, so, and those events happen after one each other. Okay, and they are not put any condition on each other. So what happened in the first experiment would not affect the outcome of the second experiment. They are independent. There is if they have dependency, there is another type of situation. So if the outcome of event A or the first experiment would affect the possible outcome of the second one, we have another type of situation. Okay, so in sequential probability, they don't affect each other. They are just in sequence. For example, we had 2 point, okay, in a sequence. The first one could be head or tails. And let's say it's a fair kind of like situation. So we have 0.5 probability of having a head, 0.5 probability of having a tail. Okay. Now, the possible outcome is either of the two happens. After that, we flip again. Okay. Now, each time for the second one, we can also have head or tail. Okay. So the situation is that either we can have head and head, head and tail, tail and head, and tail and tail. Does that make sense? Now, in sequential probability, the probabilities are going to be multiplied to each other. And it's kind of, I think, makes sense because, for example, in the first flip, you have half a chance or 0.5 probability to get a head. Okay. Now, for the second one, if you, let's say you got the head. For the second one, again, you have half a chance to get another head or a tail. Okay. So in general, you had half a chance, and again, half a chance, half of that first 0.5 to get like head and head. Does that make sense? Is that clear? So probability, when we define the probability of getting two head in a row is going to be multiplication of these two sequential condition. In this case is 0.25. Are we good? And based on what we learned before, when we said, okay, for calculating a probability, we need to develop the sample space to see, okay, what could happen? What are all the possible outcomes? If you develop the sample space, this is going to be our sample space. Please work with me. It's going to happen. Yeah. You have 4 elements in your sample space. And we said we have a first situation that means all of them are going to be equal. So basically it means 1/4 for each of those. Makes sense because even for the other perspective, that sequential probability that we run through, we had the same result. Good? Now, remember, when you have a sequential probability, what happened at the end, you have a bunch of end result. In this situation, you have those 4. Okay, the probability of all of them together should be what? What is the number? 1, because all of them create the sample space. So if for any reason you calculate something and they would not add up to 1, you know you did some mistake in the process. Okay. Now, any question? We are gonna go through those sequential probability in more detail. Okay, so it's just like an intro. Another example. Let's say we have 3 machines in our factory. We are producing resistors. We have 3 machines in our factory, each of them like a 3 manufacturing line. Okay, each of those, which we call it B1, B2, and B3, okay, either they are producing the resistors, either the resistor is properly produced, so it's functioning and we can use it, so it's accepted as a proper product, or it's not. The line failed and like is an error in a manufacturing line. Now, let's say the chance for B1, the resistor made in B1 to be accepted is 0.8. The non-accepting chance for B1 is 0.2. Okay. B2 is 0.9 and 0.1. So there's a 90% chance for B2 to have a properly produced result. Okay. For B3 is 0.6 and 0.4. Okay, which is a lousy kind of like situation. Okay. Now, we wanna randomly choose a resistor in our inventory. There is going to be a chance that that resistor either is produced by first line or second line or third line. We don't know for sure. When we choose randomly, that random resistor was made by which of those lines. But we have some probability, okay? And that could be a result of any reason. So maybe like like here, the probability of choosing from B1 product is 0.3, B2 is 0.4, and B3 is 0.3, you can assume that like B2 makes more resistors. So there is a more chance when you pick randomly in your inventory, it is like from the B2. You know what I'm saying? So these are like, so we choose a random resistor. We have 0.3 chance that this is made by B1, 0.4 chance that is made by B2, 0.3 chance that is made by B3. Now we want to see if it's accepted or not. Each of those machines has their own chance of accepting, getting like a proper result, produce a proper resistor or not. Now, the event of having a non-accepting resistor, the probability of having a non-accepting resistor that is produced in the second line in B2, we want to calculate that probability. What would be the probability when you randomly choose a resistor in your inventory? What is the probability that this is a failed product and it made by B2, the second line? Okay? Now, you can easily see that we have two events. And both of events are going to happen. So event B1 are going to happen, and event non-accepted also going to happen at the same time. What was the mathematical definition for that? When two events happen at the same time? Intersection. So basically, from mathematical perspective, when you wanted to choose one of the outcome of the sequential probability, that outcome is going to be the intersection of the two events from the two experiments. Distinguish this definition. We have two experiments. Each of them has a bunch of events in it. Like the first one has 3 events. The second one has 2 events. 2 events, you see a lot of A and N over there, but they are eventually 2 events. Okay? Now the intersection of the two would be one of the possible outcomes. Again, in a sequential probability, we just multiply the probabilities. So for example, on that situation, the probability of intersection of N and B2 is going to be 0.04. Are we good? Now, when you deal with the sequential probability, a very useful kind of like technique is to draw these lines. We call it a tree line. Okay? We are going to, again, discuss that, but I want to make sure that it's kind of like get into your head. Do not be kind of like a hero of solving in your head. You are going to make a mistake. Okay, there is a very high chance that you make a mistake if you do not use that tree diagram. There are going to be more complicated situation. It's not just that head, tail, two flip of the coin. When you know what's in a sample space. Are we good? So always in a sequential probability, draw that tree diagram, make your life way easier, and make you not basically prevent any mistakes. Now, again, all the probabilities at the end, you can calculate them, you can add them together, okay, should be added up to 1. Because that's our sample space. All the possible outcome that could happen in the two sequence, the sequence of two uncertain experiments. I'm using a lot of terminology. I wanted to for you to get used to this terminology. Before I move to that, any question about sequential? No? No. Another general type of probability that we have is a conditional probability. Now, that one is the one that we said now the second experiment is depending on the outcome of the first one. So before we said we have multiple experiments, okay, or multiple kind of like the steps. Now, what happened at the second one would not be affected by the first result. Now, here in a conditional one, That's not true. So what we define as a conditional probability is the probability of a certain outcome when we know, like we have two experiments, like experiment A and B, or event A and B in sequence, but the condition is that the event B happened. So, like let's say in the previous one, we make a condition that we know, okay, we know that B2 happened. So B1, all the branches on B1 and B3 are not going to happen. They are 0. Okay? So we condition our probability. We say that we write it like that. We call this one, this part, we read it as the probability of A condition B. That means the probability of A would happen if we know B already happened. Okay, when we say already happened, that means it's certain. Is equal, the conditional probability is going to be the equal of intersection divided by the whole probability of B in the general situation that we have before the condition. Is that clear, my statement? Now, one question. Why we divide that by B? Because we say, okay, we want to say event B happened, and now after that, event A happened. In a sequential way, we said, okay, we just multiply those probability with each other, meaning we calculate the probability of intersection of the two. Now, why we need in a conditional probability, based on the difference of sequential and conditional, why we need to divide it by B, by the probability of B? Because you're setting samples. Perfect. One of our axioms was that the probability is always between 0 and 1. That normalization axiom. We normalize our probability in the general case by considering S as a universe. So basically, the probability of any event, when you say, I wanted to find the probability of A, event A, is basically the probability of event A, I have to do that, divided by the probability of S, because this one is 1, right? So we normalize that based on the probability of S. Now, we don't mention that because it's S is 1, and yeah, the probability of S is 1, so we didn't need to mention that, but that's what's actually happened. Now, when you make a condition, that means you eliminate a lot of possible outcome from your universe. So now your universe is shrinking to that condition. But the probability distribution that you had before were normalized based on the general sample space. If you use them, they would not add up to 1 and they are not normalized. So you need to normalize them again based on your condition. And that's why, okay, you divide that by the probability of B, which is your new universe after the condition happened. Perfect. Thank you. Any question? No? Okay. Now, let's do an example. Oh, let's talk about the conditional probability. It's not an example. We know the formula. The conditional probability is equal to intersection divided the probability of the condition. Okay? Let's go through the axioms. The probability, the conditional probability, we know that it's always true, is going to be always a non-negative number. Very good. The probability of B, condition B, is 1, is very kind of like obvious. You want to say, what is the chance of B happening if we know B happened? It's certain. You know what I'm saying? And that's actually bring out that normalization, the new sample space part. So the probability of the sample space is 1. Now, this is a new sample space, the shrinked one. Now, if we have multiple events, A1, A2, and A3, where they are mutually exclusive, that means none of them would share any element. So the intersection of each pair is null set. You see, I'm using the terminology, the mathematical notation for mentioning those conditions. That was the third axiom, right? We said the probability of each of those events would be the summation of the probability of each individual, right? The probability of all union is the summation of probability of each individual. That was our third axiom. For conditional probability, you're going to have the same. If all those A1 all the way through the N or I, whatever, if they are mutually exclusive, the conditional probability of union of those, which we call it A, when B happened, is going to be the summation of each individual subset conditioned by B. Make sense? It's going to be the same. We just change the universe. Okay? Good.
Just to clarify, all the A1, A2, that's B.
They are all subsets. No, not necessarily. They are all subsets of A. Okay? Let's go back to this example. You see A is not subset of B. Okay? They share element. Actually, not necessarily. They could not share element and the probability of the condition is 0. Okay? But they could share element. They could be, there is another special situation that A could be a subset of B, but not in general condition. You can assume that. Okay? So, all we know is the union of these A1 all the way to A is going to be that capital A without a number, without any indices. Are we good? Now, if your question, if A is subset of B, okay, that means the probability of A condition B, okay, is going to be less than 1. We know that, but the probability become probability of A divided the probability of B. Why? Because the denominator was intersection of A and B, and A is a subset of B. That means the intersection of A and B is the A itself. So the probability of the condition, the probability of A condition B is going to be the probability of A divided by the probability of B. Okay? Now, if B is a subset of A, what happens? Now, when B happens, okay, the intersection of A and B is going to be the B because B is inside A. Okay, now the probability of the condition become probability of B over probability of B, which basically means B is happening. So it's going to be 1. Does that make sense? Now, we said we can't always generally assume that they have sharing any element or they are subset of each other. The general situation could be actually that the A and B are mutually exclusive. They're completely separated. If that's the case, we know that the intersection of the two would be null set, which the probability of the null set is 0. So if A and B are mutually exclusive, that means the probability of the A condition B is going to be 0. Right? Now, we talked about the sequential probability and the conditional probability. What is the difference between the two? The purpose for each of them, for the purpose of a sequential probability, is to calculating the probability of sequence of events that happening the probability of event that happening in a sequence, and they do not affect each other. For conditional probability, we calculate in the probability of an event when we know the other one happened. Okay? For representation, sequential probability, we use tree diagram. For the conditional probability, we normally use the mathematical notation. You can use the Venn diagram, but mathematical notation is also good. And the dependency was the main difference. Sequential probability, we don't have any dependency. The events are independent of each other. The two experiments in a sequence are independent of each other. But in conditional probability, the event that we want to look into that is conditioned by event B already happened. So it's depending on the result of B. Are we good? So that is for today, and this is the end of our chapter 1. I am going to post the homework 1, which is for this chapter. Make sure you submit the result before due date, and please do not postpone that to the last minute. Again, Canvas is not a very reliable system, okay? So thank you very much, and have a great rest of the day.
What's the due date for it?
I don't remember.